Have you ever stared at your smartphone right as it's dying at 1% and just kind of wondered what is actually happening inside that little glass and metal rectangle? Well, welcome to this explainer. Today, we're taking a massive zoom-out journey. We're going to start with the invisible atom and trace it straight up to the macroscopic electrochemistry that literally runs our daily lives. We are connecting the absolute smallest building blocks of the physical universe to the massive power systems that keep modern civilization humming. It's an epic journey of scale, and honestly, it's absolutely fascinating how much of our world completely relies on things we can't even see. Seriously, think about this for a second. What actually connects ancient Greece to the batteries sitting in your pocket right now? It's a bit crazy, but without humanity's earliest quest to just try and understand what fundamentally makes up a block of metal, we couldn't possibly have engineered complex things like lithium-ion cells. Basically, philosophy paved the way for physics, and physics ultimately unlocked the chemistry that powers every piece of modern technology we use. All right, let's jump straight into Section 1, the architecture of atoms. To understand power, we really have to establish our foundation down at the absolute smallest scale possible. It is honestly wild to trace this evolution. We go all the way back to 400 BC with Democritus just guessing about uncuttable matter, which he called atomio. Fast forward through John Dalton, and then to J.J. Thomson's famous plum pudding model in 1897, which basically thought atoms were just these solid spheres of positive gooey charge dotted with negative electrons. But then, in 1911, Ernest Rutherford literally shoots alpha particles at a microscopic sheet of gold foil. And this was a massive paradigm shift. He found that most of the particles zipped right through the foil, but a tiny fraction deflected violently backwards. Boom! Proof that the atom is actually mostly just empty space surrounding an incredibly dense, positively charged nucleus. But for our story today, the real magic is what's happening in that empty space. Our absolute star player here is the electron. Discovered by Thomson, this tiny negatively charged particle is staggeringly light. We're talking roughly 1,837 times lighter than a proton. To put that into perspective, if you imagine a proton as a heavy bowling ball, the electron is basically just a tiny grain of sand. This super lightweight, highly mobile particle, that is our energy currency for the entire rest of this explainer. Literally, everything we discuss from here on out is just about figuring out how to manipulate the movement of these little guys. Moving right along to Section 2, light, energy, and electrons. We know the electron is there, but now we need to see just how dynamic it can be. Max Planck completely changed the game with his quantum theory. Instead of picturing energy as a smooth, continuously flowing river, he realized it's actually more like a series of perfectly sized buckets. Energy travels in these discrete packets, photons. And what this means is that electrons aren't just sitting there being static. An electron can absorb one of these little buckets of energy and become highly energized. And the exact amount of energy in that photon, it's directly tied to its frequency. And this leads us to an absolute mind-bender, the photoelectric effect. If you strike a piece of metal with a photon of a high enough frequency, which we call the threshold frequency, you can literally knock an electron completely out of its surface. There's this minimum energy requirement known as the work function that keeps the electron bonded to the metal. But if the light hitting it clears that hurdle, the electron gets ejected instantly. This is huge because it proves we can force electrons to physically move using external energy. It is the bedrock of how we start harnessing electrical charges. Which brings us perfectly to Section 3, harnessing electrochemical power. This is where theoretical physics turns into practical chemistry. So we can eject electrons. Great. Now can we capture their flow to do actual macroscopic work? Yes, we can. We basically have two main setups ruling our world. First, galvanic cells. Think of these like your discharging battery. A chemical reaction happens naturally, spontaneously, and as electrons transfer, we force them to travel through a wire, giving us power. Then we have electrolytic cells, which do the exact opposite. They consume electrical energy to force a reaction backward. So, if a galvanic cell is like water naturally flowing down a hill to turn a water wheel, an electrolytic cell is the electrical pump forcing that water right back up the hill so we can use it again later. Take the legendary Daniels cell, for example. In this classic setup, a solid zinc anode naturally oxidizes, leaving behind electrons, while copper ions in a completely separate solution happily absorb those electrons to form solid copper. The difference in their natural desire for electrons creates a steady, highly reliable push. And if the concentrations of zinc and copper ions are perfectly equal, exactly 1 molar, this cell generates precisely 1.1 volts. But let's be real here for a second. Real-world batteries don't just stay perfectly balanced forever. That is exactly where the Nernst equation comes in to save the day. It lets us calculate the exact pressure or voltage of the cell as the reactant concentrations inevitably change. As your battery discharges, the ratio of those reactive ions shift. The Nernst equation mathematically links our standard baseline potential to that changing ratio. So treating electrical flow almost like predictable water pressure, it explains mathematically why your flashlight slowly dims as the batteries die, rather than just abruptly shutting off. And then Michael Faraday swoops in and gives us an actual mathematical superpower with his constant. He proved that exactly 1 mole of our star player, the electron, carries a massive, highly predictable charge of roughly 96,487 coulombs. This was a monumental deal because it nailed down the precise, quantitative relationship between chemistry and electricity. Thanks to this number, we know exactly how many grams of a metal will be deposited onto an electrode based entirely on how much electrical current we pass through it over a specific amount of time. It's incredibly precise. All right, grand finale time. Section 4, Batteries and Everyday Power. Let's zoom all the way out and see how this invisible electron flow powers the macroscopic stuff you use every single day. When you go to start your car, that heavy battery under the hood relies entirely on a reversible redox reaction. It uses lead plates and 38% sulfuric acid, which is amazing because it allows the battery to act as both a galvanic and an electrolytic cell. When you turn your key, the lead anode and lead dioxide cathode react with the acid to form lead sulfate, and that pushes massive amounts of electrons right through your car's starter. Then, once you're driving, your alternator pumps electricity back into the battery, reversing the reaction entirely. It's just an incredibly elegant, heavy-duty electrochemical loop. Now, fuel cells, they are beautifully simple. Think back to the Apollo space missions. They needed ultra-reliable power, so they used fuel cells that continuously fed hydrogen and oxygen gas to electrodes. Unlike a regular battery that traps all its chemicals inside and eventually just dies, a fuel cell just keeps running for as long as you feed it fuel. Hydrogen goes in one side, oxygen in the other, they swap electrons across a circuit to give you power, and the only exhaust product? Pure drinking water for the astronauts. Absolutely brilliant applied chemistry. And if we look toward a future hydrogen economy, the sheer math is staggering. Fuel cells boast an incredible 70% efficiency rate. Compare that to just 40% for traditional combustion thermal plants. Why the huge gap? Because traditional plants waste so much energy. They have to burn fuel just to make heat, to boil water, to spin a massive mechanical turbine. Fuel cells literally skip all that messy middleman work. They convert chemical energy straight into electrical energy, which makes them a massive game changer for our future energy grids. But hey, it's not all perfectly managed power grids. Sometimes this electron flow is incredibly annoying. Take corrosion. When a tiny drop of water lands on an iron bridge and oxygen is present, nature basically decides to build a tiny, destructive, unwanted battery right there on our infrastructure. The iron spontaneously acts as an anode. It loses its electrons, its structural integrity fails, and we get rust. It completely converts strong, solid iron into fragile, hydrated ferric oxide. It is just wild to step back and think about it. Understanding the absolute smallest building blocks of nature gave us the power to completely shape the modern world. We went from ancient Greeks pondering an uncuttable atom, to predicting exact voltages with complex math, to literally putting humans on the moon. And all of it happened just by learning how to direct the flow of that tiny, invisible electron. The journey from atoms to amps really is the story of modern civilization. So as we look ahead to a future of renewable energy and next-generation tech, what new frontiers do you think mastering the electron will unlock for us tomorrow?